In this video, I want to show how we can use proof by induction to show that certain expressions are divisible by given integers. And I'm going to start with this example here, which asks us to prove that un equals to 7 to the power of n minus 3 to the power of n is divisible by 4 for all n in the positive integers. So firstly, we're going to start with our base case, and we want this for all positive integers. So our base case is the first positive integer, which is n equals 1. So u1 is equal to 7 to the 1 minus 3 to the 1, which is 7 subtract 3, which is 4, which is clearly divisible by 4. So it is true in the case n equals 1. Okay, and now we want to do our inductive step. So let's write down what we're assuming. We are going to assume that this is true when n equals k. So we are assuming that the expression uk equal to 7 to the k minus 3 to the k is divisible by 4. And it might help you to say that this is equal to 4m for some integer n. And what do we want to show? Well, we want to show it is true when n equals k plus 1. So we want to show that uk plus 1, which is equal to 7 to the k plus 1, subtract 3 to the k plus 1, is divisible by 4. So let's take this expression u to the uk plus 1, and let's see how we can use our assumption to show that if this is true, then it must also be true when n is k plus 1. What we want to think about here is how can we use this assumption here? Well, what I can do here is I can rearrange this to make 7 to the k the subject. So we get 7 to the k is equal to uk plus 3 to the k, or if you prefer, 4m plus 3 to the k. I could actually do this for 3 to the k as well if I wanted to. And it doesn't really matter which we change. But notice we can now substitute this into this expression here, because 7 to the k plus 1 is just 7 lots of 7 to the k, subtract 3 to the k plus 1, and by our inductive hypothesis, this is 7 lots of uk plus 3 to the k, subtract 3 to the k plus 1. And if we expand this out, we get 7u to the k plus 7 lots of 3 to the k minus, well, this is 3 lots of 3 to the k, which is 7 lots of u to the k. And if we take a factor here of 3 to the k, we have 7 subtract 3. So this is 7 lots of u to the k plus 4 lots of 3 to the k. But we know by assumption that u to the k is divisible by 4. And this term here is also clearly divisible by 4. So this whole expression is divisible by 4 as we wanted to show. I said that you might want to let u to the k equal 4m for some integer m. Well, that might be clearer if we make that substitution, because we get 7 times 4m plus 4 lots of 3 to the k. So we can now take a factor of 4, and we can see that this is definitely divisible by 4. It's worth just pointing out here that for this to be divisible by 4, 3 to the k must be an integer. But 3 to the k is an integer when k is greater or equal to 0. So as our base case was n equals 1, we are happy here that this, because k must therefore be an integer greater or equal to 1, we're happy that this is definitely going to be an integer. So what have we done? Well, we have shown that un equals 7 to the n minus 3 to the n is divisible by 4 when n equals 1. And if un is divisible by 4 when n equals k, it is also divisible by 4 when n equals k plus 1, and so un is divisible by 4 for all n integers greater or equal to 1.